Modern cities often fail when earthquakes strike. Concrete cracks, steel bends, and rigid structures collapse as seismic energy moves violently through them. In the Andes, ancient stone walls still stand after centuries of repeated earthquakes. This contrast demands explanation. These walls were built by the Inca civilization long before modern structural engineering existed. There were no written equations, no seismic models, and no reinforced concrete. Yet many Inca structures survived earthquakes that destroyed newer buildings nearby. This forces a fundamental question. At first glance, Inca walls appear irregular and chaotic. Stones of different shapes fit together without obvious patterns or straight lines. To modern eyes, this can look unplanned or primitive. In reality, the irregularity is intentional. Most modern buildings rely on rigidity to remain standing. They are designed to resist movement and stay fixed in place. When seismic energy enters these structures, it becomes trapped. Cracks and failures follow quickly. Earthquakes do not destroy buildings because of weight alone. They destroy them through vibration and repeated motion. Seismic waves travel through structures, amplifying stress at weak points. The Incas learned this through experience. Instead of resisting movement, Inca walls were designed to accommodate it. Motion was not treated as a failure. It was treated as an expected condition that had to be managed. Inca structures use dry stone masonry as their core technique. Stones are placed directly against one another without mortar binding them together. This creates a system that is firm, but not brittle. Each block can respond independently to motion. When an earthquake begins, individual stones react immediately. They shift, rotate, and slide by tiny amounts measured in millimeters. This controlled movement absorbs seismic energy before it can build up. The wall behaves more like a system than a single object. As the shaking subsides, gravity takes control of the structure. The stones settle back into their original positions. Contact surfaces lock together again through friction and weight. The wall restores itself without permanent damage. This behavior is known in modern engineering as energy dissipation. Today, complex mechanical systems are designed to achieve it. The Incas achieved the same outcome using geometry, mass, and patience. The shape of the stones is critical to this behavior. Inca stones are rarely square or rectangular. Instead, they are polygonal, with many angled faces and interlocking edges. Each angled face increases friction between neighboring stones. Each contact point redirects force in a different direction. There is no single straight path for stress to travel through the wall. As seismic energy moves through the structure, it is repeatedly broken apart. Motion is redirected, weakened, and dispersed. Cracks cannot propagate cleanly or predictably. The stones were shaped with extreme precision, but not for decoration. Precision ensured even contact between surfaces. This allowed movement to occur in controlled ways rather than violently. Tight joints reduced sudden impacts during shaking. Stones did not slam into each other or separate dangerously. Instead, motion remained smooth and incremental. This minimized internal damage. Another critical feature is the slight inward tilt found in many Inca walls. The walls lean gently toward the interior of the structure. This design choice directly affects stability. By shifting the center of mass inward, gravity becomes a stabilizing force. During an earthquake, the wall is pulled back toward itself instead of tipping outward. Balance replaces resistance as the primary defense. Modern engineers recognize this principle immediately. Stability does not come from stiffness alone. It comes from controlled balance under changing forces. Inca builders also avoided vertical alignment of stone joints. Stones were staggered so seams never lined up directly above one another. This eliminated continuous weak planes. Without straight vertical seams, seismic energy could not move upward efficiently. It was forced to change direction repeatedly. Each redirection reduced its destructive potential. Foundations were treated with the same care as walls. Where possible, structures were anchored directly into bedrock. This minimized amplification from softer soils. On uneven ground, stones were carved to match the shape of the rock beneath them. This created intimate contact between wall and earth. The structure became part of the landscape itself. Mortar is common in modern construction, but it behaves poorly during earthquakes. It cracks under stress and transfers force unevenly. The Incas learned this lesson empirically. Dry stone masonry behaves differently. It allows controlled movement without catastrophic failure. Each stone participates in a flexible system rather than acting as a rigid unit. Earthquakes were common in the Andes. The Incas did not learn from a single disaster. They learned from many events over long periods of time. Failed structures provided lessons. Successful designs were repeated and refined. Engineering knowledge evolved through observation rather than theory. This knowledge was never written down. It was preserved physically, embedded in stone and layout. Each wall recorded what worked and what did not. When an earthquake strikes an Inca wall, the entire structure vibrates as a coordinated system. Stones shift relative to one another in predictable ways. Energy is absorbed internally rather than released catastrophically. Some stones rotate slightly. Others slide and relock into position. The system remains coherent even during intense shaking. This self-correcting behavior is what makes the walls extraordinary. They are not static objects frozen in time. They are dynamic systems designed for a moving world. Modern base-isolated buildings use bearings and sliding mechanisms to achieve similar results. These systems are expensive and technologically complex. The Inca solution required none of them. Even doorways and windows were engineered with earthquakes in mind. Openings were trapezoidal rather than rectangular. Shape itself became a safety mechanism. Rectangular openings concentrate stress at sharp corners. Trapezoids redirect force downward and outward. This greatly reduces the risk of collapse. This design logic appears consistently throughout Inca architecture. Nothing was arbitrary or purely aesthetic. Every shape served a structural purpose. Cusco offers clear evidence of this engineering logic. Colonial buildings collapsed during major earthquakes. Inca foundations beneath them remained intact. Spanish builders unknowingly relied on Inca engineering to keep their own structures standing. Ancient stonework supported modern walls that could not survive on their own. Modern seismic studies confirm this behavior. Measurements show that dry stone masonry dissipates energy more effectively than rigid masonry systems. Physics aligns with archaeological evidence. Engineers now study Inca walls as functional systems. They are no longer treated as curiosities or anomalies. They are studied as successful structural solutions. The genius of Inca engineering lies in restraint rather than excess. Builders did not overbuild or overcomplicate. They built exactly what was required to survive. Every stone had a specific role within the wall, shaped and placed with intention. Angles were chosen to maximize friction, stability, and energy dispersion. Nothing was decorative, and nothing was wasted. Every decision supported long-term survival. This was not engineering designed to dominate nature. It was engineering designed to cooperate with it. The walls respond to the ground beneath them instead of opposing it. Instead of resisting earthquakes, Inca structures adapt to them. Motion becomes part of the design rather than a threat. Stability emerges through flexibility. This philosophy is only now returning to modern architecture. Flexible systems outperform rigid ones in unstable environments. The Incas understood this long before formal seismology. Their walls act as lessons carved into stone. Each structure reflects observation, failure, and improvement over generations. Knowledge persisted without writing. No written equations survive from the Inca world, and no architectural blueprints remain. Yet the logic of their engineering is visible in every joint and angle. The stones themselves preserve knowledge that words never recorded. These walls still stand not because they are unbreakable. They stand because they are adaptable. Strength emerges from understanding rather than force. Inca engineering did not seek permanence through rigidity. It sought survival through balance, motion, and gravity. This mindset shaped every structure they built. These walls remind us that technology is not defined by complexity alone. It is defined by how deeply a problem is understood. Simplicity can be the result of mastery. The Incas understood the ground beneath their feet and the forces acting upon it. They observed nature closely and built accordingly. Their solutions were shaped by reality. In a world that moves, the structures that last are not the ones that resist motion. They are the ones that move intelligently with it. This is the lesson carved into every Inca wall. That is why these walls still stand today. And that is why their engineering continues to matter in the modern world.